On October 3rd, 2025, spacecraft orbiting Mars turned their cameras towards something no human had ever witnessed before. Scientists around the world held their breath as the European Space Agency's ExoMars Trace Gas Orbiter snapped pictures of a visitor from the stars, a comet from outside our solar system called 3I Atlas, hanging in space about 30 million kilometers away from the red planet. What they saw that day was beautiful and strange, a fuzzy white dot surrounded by a glowing cloud of gas and dust. But this wasn't just any comet passing through our neighbourhood. This was something that made scientists scratch their heads, because it was doing something almost no comet had ever done before. And when we dig into the story of how it got here, what it's made of, and what it might teach us about the universe, we stumble onto one of the most fascinating mysteries the cosmos has handed us in recent years. Let's start at the very beginning, though. Before 3 Atlas showed up, there were only 2 other interstellar visitors that humanity had ever confirmed. The first one, called Oumuamua, sailed through our solar system back in 2017, moving so fast that it was gone almost before we noticed it. Then in 2019, another one called 2I Borisov came tumbling through. But 3I Atlas is different. It's bigger, it's active in ways we didn't expect, and it's doing something with its tail that's got astronomers debating what's really going on out there in the cosmic dark. Here's where our story truly begins. On July 1st, 2025, at an observatory called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, sitting high up in the mountains of Chile in a place called Rio Hurtado, a robotic telescope was doing what it does every single night. It scans the sky, looking for asteroids and space rocks that might pose a danger to Earth. Think of it like a guardian with incredibly sharp eyes, watching the neighbourhood for anything unusual. That night, something unusual appeared. The telescope spotted an object moving across the stars in a way that caught the attention of the computers analysing the data. Something was off. This object was travelling too fast and on a trajectory that didn't match anything from our solar system. Within days, astronomers around the world were looking at this discovery, confirming what the initial data suggested. This was truly an outsider, a comet that had drifted through interstellar space for billions of years before accidentally wandering into our solar system. When we talk about interstellar objects, we're talking about something almost impossibly rare. Our solar system, the sun and all the planets and moons and asteroids and comets circling around it, is kind of like a giant family, all born together from the same cloud of dust and gas around 4.6 billion years ago. Everything here shares a common origin story. But interstellar objects are true strangers, born around other stars light years away, and somehow knocked out of their home systems by cosmic events we can only guess at. Some might have been flung out by collisions, others might have been ejected by a nearby star passing too close. Whatever happened, they've been drifting alone through the cold, dark space between stars for eons. The names of these objects tell their story. Oumuamua and 2I Borisov both came from beyond our solar system, but when 3 Atlas was officially named, that I at the beginning meant interstellar, an outsider. The 3 meant it was the third one confirmed by humanity. And Atlas? Well, that's just the name of the telescope that first spotted it. There's a whole naming system for comets developed by the International Astronomical Union, which is basically the official club of people around the world who keep track of all this stuff. It used to be that comets were just named after whoever discovered them. You'd have Comet Johnson, or Comet Chen, or something like that. But now we use this more systematic approach that helps us keep track of thousands of objects efficiently. Still, there's something special about knowing that 3I Atlas carries within its very name the place where humans first caught sight of it, a little robotic telescope in Chile that was just doing its job watching the sky. Now here's where things get really interesting. This comet was discovered on July 3rd, but it's been moving through space for billions and billions of years before that. Based on its speed and the path it's taking, astronomers have figured out something remarkable. 3I Atlas might be up to 3 billion years older than our entire solar system. Let that sink in for a moment. Our solar system has been around for 4.6 billion years. This comet might have been drifting through the galaxy for 7 or 8 billion years. It's ancient beyond ancient, an emissary from a time when the universe was much younger and our star system didn't even exist yet. The speed at which this comet is travelling tells astronomers a lot about where it came from. When 3I Atlas entered our solar system, it was moving at about 58 kilometers per second relative to the Sun. That's roughly equivalent to 36 miles per second, or if you want to think about it in more everyday terms, it's about 129,000 miles per hour. That's incredibly fast. For comparison, the previous interstellar object Oumuamua was only moving at about 26 kilometers per second, and 2I Borisov at 32 kilometers per second. This comet is speeding through our neck of the woods faster than its predecessors, which suggests it's been travelling through the galaxy for an incredibly long time, gathering cosmic dust and tiny pebbles as it went, or perhaps it was ejected from its home system with more force. One of the most important facts about 3I Atlas, which tells us a lot about how it's behaving right now, is that its path through our solar system isn't circular like the orbits of normal comets. Instead, it follows what's called a hyperbolic orbit, which is more like a giant open curve. Picture a ball rolling along a track that never closes back on itself. It just keeps going, coming in one way and going out another, never to return. This tells us definitively that this comet is not trapped in our solar system. It's just passing through on a cosmic journey, and once it swings around the sun, it will eventually drift back out into the deep space between stars, never to be seen by humans again. Well, unless we build faster spacecraft and chase after it, which is probably not happening anytime soon. What's fascinating is that 3I Atlas isn't coming from a random direction. If it were a truly random visitor from interstellar space, you'd expect it to approach from all different angles. But instead, it's coming from the direction of the constellation Sagittarius, heading down from above the plane of our solar system in a way that's almost perfectly aligned with the orbits of our planets. There are billions of stars in that direction. We're talking about looking toward the center of our Milky Way galaxy, where stars are packed incredibly densely together. Figuring out which exact star system this comet came from is going to take a lot of detective work and many years of study. Scientists have already started working on this puzzle, trying to trace the comet's path backward through space and time to see if they can figure out where it originated. When 3 Atlas made its closest approach to Mars on October 3, 2025, it came within about 30 million kilometers of the red planet. That's farther than the distance from Earth to the Sun, but close enough in cosmic terms that spacecraft orbiting Mars could turn their instruments toward it and capture data. The European Space Agency had prepared for this moment. 2 spacecraft that were already there doing their regular work, the ExoMars Trace Gas Orbiter and Mars Express, both shifted their focus to observe this special visitor. The challenge, though, was immense. Both of these spacecraft were designed to photograph the bright surface of Mars from just a few hundred to a few thousand kilometers above it. Trying to use those same cameras to capture a dim, distant comet 30 million kilometers away was a bit like trying to photograph a firefly from the other side of town using binoculars designed to read a newspaper. The ExoMars Trace Gas Orbiter got the best images, using a camera system called CASIS, which stands for the Color and Stereo Surface Imaging System. The spacecraft managed to capture a series of pictures showing the comet as a slightly fuzzy white dot against the background of stars. The nucleus of the comet itself, the solid, icy rocky center, was too small and too far away to see in detail. It would have been like trying to see a mobile phone on the moon from Earth. But what the cameras could see was the coma, the glowing atmosphere of gas and dust that surrounds the nucleus. The coma of 3I Atlas was several thousand kilometers across, a giant halo of material released from the comet as the sun's heat warmed it. Scientists were amazed that the comet was already so active when Mars was observing it, because 3I Atlas still had weeks to go before it would reach its closest point to the Sun. Speaking of which, the closest approach to the Sun, called perihelion, happened on October 29, 2025. At that point, 3I Atlas came within about 203 million kilometers of the Sun, which placed it between the orbits of Earth and Mars, closer to the Sun than Earth normally travels. To give you a sense of scale, imagine the Sun sitting in the middle of a circle, with Earth's orbit as one circle and Mars's orbit as a bigger circle farther out. That spot where 3I Atlas came closest to the Sun was somewhere between those two circles, closer to the Mars side, and the journey closer and closer to the Sun was making the comet more and more active. All that distant heat was warming the frozen gases trapped inside the comet's nucleus, causing them to vaporize, to turn from solid ice into gas, carrying dust particles along with them. The composition of 3I Atlas is where we start to see something truly unusual about this visitor. When the James Webb Space Telescope, one of the most powerful telescopes humanity has ever built, pointed its instruments at 3 Atlas, it discovered that this comet is unusually rich in carbon dioxide. That's the gas that plants breathe in during photosynthesis, the gas that makes soda fizzy, and it's also a greenhouse gas in our atmosphere. Finding so much carbon dioxide in 3I Atlas was significant because most comets from our solar system don't have quite so much of it. The comet also contains water ice and water vapour, carbon monoxide, and something called carbonyl sulfide. These are all frozen gases that become active when heated by the sun. But the carbon dioxide seems to be the main driver of this comet's activity, the fuel that's making it behave in unusual ways. Even more surprising, scientists using ground-based telescopes like the Very Large Telescope in Chile discovered that 3I Atlas is releasing cyanide gas and atomic nickel vapour. Now, cyanide is a poison that exists in some natural materials, and nickel is a metal. Finding these elements being released from the comet was interesting, but then scientists noticed something even stranger. There was plenty of nickel, but hardly any iron. In our normal understanding of how the universe works, iron and nickel are almost always found together. When massive stars explode as supernovae, they create both elements together. You almost never find nickel without iron in natural space objects. But 3I Atlas was showing this unusual separation. Some scientists noted that on Earth, when we refine nickel industrially, we use a special process called nickel carbonyl formation that separates nickel from other elements. Finding this signature in a comet from another star system raised eyebrows, though most mainstream scientists offer natural explanations for why this separation might occur through different physics in a cold, distant comet. The water activity from 3I Atlas was another surprise. NASA's Swift Ultraviolet and Optical Telescope observed the comet in July and August 2025 and detected the faint ultraviolet signature of hydroxyl, which is a sign that water vapour was escaping from the comet. But here's the unusual part. The comet was actively releasing water vapour when it was still nearly 3 times as far from the Sun as Earth is. At that distance, according to what we know about comets, the Sun's heat should not be strong enough to turn water ice directly into gas through the process we call sublimation. Comets usually don't become active water producers until they get much, much closer to the Sun. So the fact that 3I Atlas was already losing water at such a great distance suggested that something else was going on. Maybe the carbon dioxide was sublimating first, exposing fresh ice that then released water, or perhaps there was some other process at work. But the most shocking thing about 3I Atlas wasn't its chemistry or its speed, or even that it came from another star system. The most shocking thing was the bizarre behaviour of its tail, which became the focus of intense study and debate among astronomers throughout 2025. In normal comets, the tail always points away from the Sun. Here's why. As a comet approaches the Sun, the solar wind, which is a stream of particles flowing out from the Sun, and the radiation pressure from the Sun's light push the dust and gas away. Imagine standing in a strong wind. The wind pushes you backward. The Sun's radiation works similarly on comet material, pushing it outward into a tail that streams away from the Sun like a flag waving in the breeze. It's one of the most fundamental and predictable behaviours in the solar system. You could count on it. Every comet ever observed has had its tail pointing away from the Sun, at least the dust tail. Until 3I Atlas. When astronomers using the Hubble Space Telescope looked at 3I Atlas on July 21st, 2025, they saw something they had never seen before. The comet had what's called an anti-tail or anti-solar tail. Instead of pointing away from the Sun, the extended glow of the coma, the fuzzy cloud around the nucleus, was pointing toward the Sun. It was literally backwards. Imagine waving a flag in the wind, and instead of the flag trailing behind you, it was pointing backward toward you. That's what was happening. Researchers who studied the Hubble images carefully found that this anti-tail had an elongation that, when you correct for the angle from which they were viewing it, might extend 10 times longer in one dimension than another. It looked almost like a jet, a narrow stream of material pointing right at the Sun. Scientists had to think hard about what could explain this. Dr. David Jewett of UCLA and his team proposed an explanation that seemed to make sense. They suggested that the anti-tail was due to preferential sublimation of ice on the side of the nucleus that was facing the Sun. In other words, the Sun was heating up one side of the comet much more than the other side. On the hot Sun-facing side, ice was sublimating rapidly, creating a burst of outgassing that blasted particles into space. On the night side of the comet, the side facing away from the Sun, it was much colder, and little to no sublimation was happening. This asymmetry created an imbalance in where the dust was coming from. Most of the ejected material was coming from the sun-facing side, and when that material was released, some of the smallest, finest particles, particularly ice grains made of water, scattered light in a way that made them visible pointing toward the sun. It was a natural physical explanation for an unusual phenomenon. But then something even more remarkable happened. Between July and September 2025, as 3i Atlas continued to approach the sun and become heated more intensely, observations showed that the anti-tail was changing. By September, when new images were taken using the Nordic Optical Telescope in the Canary Islands, Spain, and confirmed by other observatories like the Keck Telescope and the Gemini South Telescope, scientists saw that the anti-tail had vanished. In its place, a normal comet tail had formed, pointing away from the sun like a regular comet tail should. This wasn't a minor adjustment or a subtle shift, it was a complete reversal, a transformation so dramatic that some scientists called it a complete inversion of its mass flow geometry. Think about what that means. The comet had done something unprecedented. For the first 2 months it was producing a jet of material pointing toward the sun. Then, as it got closer to our star, that behaviour completely flipped, and it started producing a normal tail pointing away from the sun. It was as though the comet had thrown a switch, changing its mode of operation. Researchers who studied this transformation proposed a detailed physical model to explain it. As 3i Atlas approached the sun, the heat increased exponentially, meaning it didn't just get a little hotter, it got vastly hotter. This intense heat caused the sublimation rate of carbon dioxide to increase dramatically. Carbon dioxide ice, when it sublimates, releases water ice fragments. At first, when the comet was farther away and the heating was less extreme, water ice particles formed by this CO2-driven outgassing were small and fragile. These tiny ice crystals reflected sunlight very efficiently, creating a visible glow pointing back toward the sun, the anti-tail. But as the comet got closer and the heat increased, the fragments being produced became different. The residence time of these fragments, the amount of time they survived before being destroyed by solar radiation, decreased dramatically. Meanwhile, larger dust particles and more robust grains survived longer. These particles, being heavier and less dependent on the light from the sun, were pushed into a normal tail pointing away from the sun by the solar wind and radiation pressure. The transition from anti-tail to normal tail reflected this shift in what kinds of particles dominated the comet's outflow. It was beautiful physics, elegant in its explanation, and it made sense based on everything we understand about how comets work. But not everyone was satisfied with this explanation. Some scientists, most notably Dr. Avi Loeb of Harvard University, pointed out that while this model might explain some aspects of what we were seeing, there were still anomalies that needed addressing. Loeb has made a career of pushing scientists to think carefully about whether truly unusual observations might indicate something beyond our normal categories. He's not suggesting recklessly that every strange object is alien, but he does argue that when we see something that doesn't fit the expected pattern, we should examine it carefully before dismissing it. Loeb ranked 3i Atlas on what he called the Loeb scale, a measurement system he developed to assess how likely an interstellar object is to be technological rather than natural. On this scale, 0 means definitely a natural comet, and 10 means probably an artificial construct. Oumuamua, the first interstellar object, initially scored higher on this scale because it seemed to lack a visible coma and acted strangely. But when it was studied more carefully, the mysteries were explained, and it moved down the scale. 2i Borisov was clearly a natural comet from the start. As for 3i Atlas, Loeb rated it at 4 out of 10, suggesting it has increasingly anomalous characteristics. He based this rating not just on the anti-tail but on a combination of factors: the unusual orbital alignment, the unusual size and mass, the strange chemical composition, and the unprecedented tail reversal. Here's what makes Loeb's perspective interesting, even if many mainstream astronomers don't agree with his conclusions. He points out that every interstellar comet so far has been a surprise. Oumuamua was dry, lacking water. 2i Borisov was rich in carbon monoxide. Now 3i Atlas is giving up water at distances where standard comet theory says it shouldn't be active. Each one is forcing us to revise what we thought we knew about how planets and comets form around other stars. When you keep finding that your expectations are wrong, it's worth pausing and making sure you're not missing something important. But the mainstream astronomical community, while acknowledging that 3i Atlas is unusual, has settled on the natural explanation. The transformation from anti-tail to normal tail, they argue, is exactly what you'd expect as a comet approaches the Sun, and the physics of the outgassing process shifts in response to increased solar heating. It's not a sign of artificial course correction or braking and acceleration maneuvers, it's just physics, albeit physics playing out in a rather extreme environment that we don't get to observe very often. The other observatories didn't sit idle while this debate was happening. NASA's Perseverance rover on Mars, NASA's Curiosity rover, and NASA's Mars Reconnaissance Orbiter all attempted to observe 3I Atlas during its close approach to Mars. The Mars Reconnaissance Orbiter's high-rise camera, which has incredible resolution and can image objects from Mars orbit with detail showing features about 30 meters across, was positioned to capture images of 3I Atlas on October 2nd, 2025. Those images, when they're eventually released, could provide unprecedented detail about the comet's structure, potentially showing the nucleus itself rather than just the glowing atmosphere around it. The images haven't been made publicly available as of late October, but they're expected to offer the clearest view of any interstellar comet yet captured. The activity level of 3I Atlas has been staggering. Scientists have measured that the comet is losing about 150 kilograms of material per second when it's at peak activity near the Sun. Let me put that in perspective for you. That's like if you collected all the water pouring out of about 35 fire hoses, all running at full blast, and that entire amount was being launched into space from a rocky nucleus less than 5 kilometers wide. Some estimates suggest the nucleus might be between 0.3 and 5.6 kilometers in diameter, with the most likely size being less than 1 kilometer. If it's on the smaller end of that range, then the amount of material it's ejecting is phenomenal. At the rate it's losing material, even the smaller estimates would have the comet shedding millions of tons during its passage through the inner solar system. Here's a question that scientists have been asking. Where did all this material come from? The comet hasn't been anywhere near the Sun for billions of years, so all the gas and dust being released right now comes from the comet's interior, from frozen volatiles locked inside the nucleus. This means the nucleus must be incredibly rich in these frozen gases, far richer than many comets from our own solar system. It's like a frozen time capsule from a different star system, carrying chemical signatures and materials that formed under completely different conditions than our solar system's comets. In November 2025, after the comet had passed behind the Sun from Earth's perspective and become temporarily invisible from our planet, a new opportunity for observation came up. The European Space Agency's JUICE mission, which stands for Jupiter Icy Moons Explorer, was positioned to observe 3I Atlas. JUICE is a spacecraft that's on its way to Jupiter to study that planet's moons, particularly the icy moons that might harbour conditions suitable for life. But its path through the solar system brought it to a position where, in November 2025, it could turn its instruments toward the comet. By that time, 3I Atlas would have passed through its closest point to the Sun and would be in a very active state, with intense solar heating causing maximum outgassing. JUICE's cameras and spectrometers would provide valuable data about the comet's composition and activity level in this crucial phase. Scientists don't expect to receive and analyze the data from these observations until February 2026, but when it arrives, it will provide crucial information about how 3I Atlas behaves at its most extreme point. The closest approach of 3I Atlas to Earth is scheduled for December 19, 2025. However, it's important to understand that closest in cosmic terms is still incredibly far. Even at its nearest point, 3I Atlas will be about 240 million kilometers away, which is more than 1.5 times the distance from Earth to the Sun. In other words, it will be as far from us as the Sun is, and then further. There's absolutely no danger to Earth from this object. It couldn't possibly impact our planet or harm us in any way, but the distance is close enough in astronomical terms that we'll be able to observe it with telescopes and potentially gather more data about its properties and behavior. One fascinating possibility is that two spacecraft might pass through the comet's tail material around the time of its closest approach to Earth. NASA's Europa Clipper and the European Space Agency's Hera spacecraft are both in regions of space where, due to the comet's trajectory and their own orbital paths, they might intersect with the comet's tail. If this happens, they could gather samples of material from the comet and measure its chemical composition directly, getting information that ground-based telescopes could never provide. It would be like having a space probe dip through a river and collect water samples to analyze, rather than just looking at the river from a distance and trying to infer what's in it based on how it reflects light. The visibility of 3I Atlas from Earth has been limited. The comet is too faint to see with the naked eye or even with binoculars. You need a telescope to see it, and even then, you need a fairly good telescope. As it approaches the Sun, it comes between Earth and the Sun in our sky, and the Sun's glare makes it impossible to see from our planet. After perihelion, it will emerge from the glare and become visible again in the early morning sky during November and December 2025, appearing in the constellation Virgo. Astronomers and serious sky watchers with appropriate equipment were encouraged to track it during these windows, contributing observations to the global scientific effort to understand this mysterious visitor. The mystery of where 3I Atlas came from is still being investigated. One team of scientists led by Xavier Perez Couto of the University of A Coruña in Spain has tried to trace the comet's path backward in time to see where it might have originated. They worked backward about 10 million years through space, trying to figure out which star system might have ejected this object. Imagine trying to work backward through time to find where a specific car came from, knowing only its license plate and current location. That's roughly the challenge these scientists face. The comet came from the direction of the constellation Sagittarius, which points toward the centre of our Milky Way galaxy, where stars are incredibly densely packed. Working out which specific star system it came from requires careful modelling of stellar motions, the gravitational influences it might have experienced, and the current and past trajectories of nearby stars. It's detective work on a cosmic scale. What we do know is that 3I Atlas carries within its composition clues about a different star system, a different solar system somewhere out in the Milky Way galaxy. When comets form around other stars, they form under different conditions, with different available elements and different processes than what happened around our Sun. The prevalence of carbon dioxide in 3I Atlas suggests it formed in a region where CO2 was abundant. The presence of cyanide and nickel in unusual proportions suggests different chemical processes were at work. The chemistry of a comet is like a fingerprint or a passport. It tells us something about where it came from. Some scientists have speculated about whether studying interstellar objects like 3I Atlas might eventually help us understand whether life could be transported between star systems. This is a concept called panspermia. Could comets like this, if they happen to carry microbial life or organic compounds formed in one star system, potentially travel to another star system and seed the beginning of life there? It's an intriguing idea, but there's no evidence that 3I Atlas carries life, or even that the journey through space would allow life to survive. The radiation and extreme temperatures of space are harsh environments, but the molecules and compounds in objects like 3I Atlas do teach us what kinds of organic material exist in the universe, which gives us insight into chemistry across different solar systems. The names of the first 3 interstellar objects have an interesting history. Oumuamua, which means scout in Hawaiian, was named by astronomers in Hawaii who first studied it carefully. 2I Borisov was named after the citizen scientist Gennady Borisov who discovered it. But 3 Atlas doesn't honour a person, it honours the instrument and the location. ATLAS stands for the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes. The first ATLAS telescope to spot 3I Atlas was located in Rio Hurtado, Chile, in the Atacama Desert, one of the driest places on Earth. That location was chosen specifically because of how clear and dry the skies are there, ideal for astronomical observation. The telescope sits at high altitude, above much of the atmosphere, where it can see the stars more clearly. This partnership between technology and geography, the precise robotic telescope and the clear mountain skies of the Chilean desert, is what led to the discovery of this remarkable object. Now, let's talk about why 3I Atlas matters. Beyond just the fascinating science, every time we study an interstellar object, we're studying a messenger from another part of the galaxy. We're gathering information about how planets and comets form around other stars, about the diversity of planetary systems in the universe, and about the processes that have been shaping galaxies for billions of years. Each interstellar object that we detect and study is like receiving a message from the distant universe, telling us about conditions in a place we could never visit, under circumstances we could never replicate in our laboratories. The fact that we've now detected 3 interstellar objects, Oumuamua, 2I Borisov and 3I Atlas, suggests that these objects are not vanishingly rare. Before the first detection, astronomers weren't sure how many interstellar comets might be drifting through the solar system at any given time. After the first discovery, some models suggested maybe 1 or 2 pass through every 100 years or so. But now that we've found 3 in less than a decade, those estimates might need to be revised upward. There could be many more interstellar visitors passing through our solar system that we haven't detected yet because they're too small or too dim. This realization has profound implications. It means that our solar system isn't isolated, it's constantly interacting with visitors from the broader galaxy. Sometimes these visitors are comets, maybe sometimes they're other things. The discovery of these interstellar objects tells us that the universe is more interconnected than we might have thought, with material flowing and mixing between different star systems over billions of years. One of the things that makes 3I Atlas special is its unusual orbital characteristics. As we mentioned, it's coming into our solar system from a direction almost perfectly aligned with the plane of the planets, the ecliptic plane. Most random visitors from interstellar space would come from random directions, but 3 Atlas came from above the ecliptic plane at an angle of about 175 degrees retrograde, meaning it's coming at the solar system from a tilted direction, but still roughly in the same plane as the planet's orbit. The probability of this happening by chance alone is actually quite low. If interstellar objects were arriving at random angles, you'd expect many of them to come from directions wildly tilted above or below the ecliptic. But 3I Atlas didn't. Some scientists find this alignment interesting, though the mainstream explanation is that it's a coincidence, or perhaps that the geometry of how our galaxy's structure influences where stellar systems are located makes certain angles more likely. The mass of 3I Atlas, estimated based on its brightness and how fast it's losing material, is enormous compared to our previous interstellar visitors. Some estimates suggest it could be 1 billion times more massive than 1I Oumuamua. If the nucleus is on the larger end of estimates, around 5 kilometers in diameter, and if it has a density similar to other comets in our solar system, then we're talking about an object with a mass in the range of tens of billions of tons. That's what's remarkable about this comet. It's genuinely big. For context, the mass of a large asteroid like Ceres, one of the largest objects in the asteroid belt between Mars and Jupiter, is about 9.4 times 10 to the 20 kilograms. 3 Atlas, if our estimates are correct, might be approaching comparable masses. This size itself is unusual. Smaller objects should be more common in the universe than larger objects, simply by the laws of statistics. Finding such a relatively large object so soon after we started looking is surprising. As we approach the end of October 2025 and the comet nears perihelion, the scientific community around the world is watching carefully. Telescopes from every continent, observatories in space, and spacecraft scattered throughout the solar system are all monitoring this remarkable visitor. The data being collected during this period will be analysed for years to come, yielding insights into the composition, structure, and behaviour of materials formed in a completely different star system. Let's think about what happens next. After perihelion on October 29th, 3I Atlas will begin its retreat from the Sun. It will continue to brighten somewhat, reaching its closest approach to Earth on December 19, 2025, still shining at around magnitude 12 to 13, depending on how much material it's still losing. That's still invisible to the naked eye, still requiring a telescope to see, but it will be observable by dedicated astronomers and skywatchers with proper equipment. After Earth, the comet will continue its trajectory through space, potentially passing close to Jupiter in March 2026, and then it will gradually recede from the inner solar system, heading back out into the deep cold of interstellar space. But before the comet leaves us entirely, there's another important passage ahead. On November 3, 2025, 3I Atlas is scheduled to pass within about 97 million kilometers of Venus. Venus is our closest planetary neighbor to the Sun, and 3I Atlas will come nearly as close to Venus as it came to Mars. After that, the comet will continue its journey through the inner solar system, and eventually, after passing near Jupiter in early 2026, it will have enough energy to escape the Sun's gravity permanently. Unlike the comets that belong to our solar system, which are bound to the Sun and return periodically or stay in regions like the Oort cloud, 3A Atlas will eventually leave us behind entirely. It will have borrowed a little time in our neighbourhood, gathered some energy from the Sun's gravity, and then headed back out into the galaxy from whence it came. We don't know if 3I Atlas will ever encounter another star system. It might drift through the galaxy for another few billion years, maybe longer, drifting in the cold darkness between stars. Or it might eventually be gravitationally captured by another star, beginning a new phase of its existence in a different cosmic location. The universe is vast beyond human comprehension, and the timescales are enormous. Billions of years are like days on the cosmic calendar. The debate about 3I Atlas's nature will probably continue for years. Was it a natural comet, behaving according to the laws of physics that we understand? Or was there something more unusual about it that we didn't quite capture? The scientific mainstream has settled on the natural explanation, but people like Avi Loeb continue to ask questions and point out anomalies, suggesting that we keep looking carefully and not dismiss things too quickly just because they're unusual. In the end, both perspectives, the cautious skepticism of the mainstream and the open curiosity of the outliers, are important for science. The mainstream prevents us from jumping to wild conclusions without evidence. The outliers prevent us from becoming so locked into our assumptions that we miss genuine discoveries. One fascinating aspect of 3I Atlas that deserves more attention is its role in expanding our understanding of exoplanetology, the study of planets around other stars. When astronomers study exoplanets, they do so from a distance, using techniques like watching how a star's light changes as a planet passes in front of it, or measuring wobbles in a star's motion as planets orbit it. Direct observation of exoplanets is possible but difficult. The planets are faint compared to their stars, and detecting them requires special instruments and clever techniques. But comets from other star systems carry direct samples of the material from those star systems. By studying 3I Atlas's chemistry, composition and structure, we're learning what kinds of materials exist in other planetary systems. We're learning something about the conditions that exist around other stars. In a sense, 3I Atlas is like a geological sample returned from another world, except it didn't come from another world in our solar system, it came from another solar system entirely. The detection of 3I Atlas also highlights the importance of automated surveys and continuous sky monitoring. The Atlas survey that discovered it, as well as other surveys like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory, with its legacy survey of space and time, are designed to scan the entire night sky repeatedly, looking for changes and new objects. These surveys will likely discover many more interstellar objects in the coming decades. Some might be smaller and harder to observe, others might be larger and more active than 3I Atlas. Each one will teach us something new about the broader universe beyond our solar system. In many ways, 3I Atlas represents a new era in astronomy, the era of interstellar object studies. For all of human history until 2017, we had no confirmed interstellar objects to study. Now we have 3, with probably many more to come. This opens up entirely new research questions. How many interstellar objects pass through our solar system? What's their composition compared to the comets that form locally? What does their presence tell us about how common Earth-like planets might be around other stars? Can we eventually send spacecraft to intercept and study these objects up close? That last question is particularly interesting. So far, we've been studying 3I Atlas and previous interstellar objects from a distance, using telescopes here on Earth and spacecraft in our solar system. But the speed at which these objects are travelling makes it difficult for us to catch up with them using current technology. 3I Atlas entered our solar system moving at 58 kilometers per second. Our fastest spacecraft, like the Parker Solar Probe which studies the Sun, can reach speeds of about 200 kilometers per second, but only because it's falling toward the Sun and can use the Sun's gravity to accelerate. Chasing down an interstellar object that's already passing through our solar system and planning to escape would require technologies we haven't yet developed. But who knows what might be possible in 50 or 100 years? Maybe future generations of humans will have spacecraft fast enough to catch up with these visitors and study them directly. The discovery and study of 3I Atlas has also renewed public interest in astronomy and space exploration. Stories about mysterious visitors from other star systems capture people's imagination. Even though the scientific mainstream conclusion is that 3I Atlas is a natural comet, not an alien spacecraft, the possibility alone was enough to get people excited about looking up at the sky and thinking about the cosmos. There's value in that excitement. When people are inspired by science, when they're curious about the universe and eager to learn more, that curiosity can lead to deeper engagement with science education and careers in astronomy and space exploration. Teachers around the world have used 3I Atlas as a teaching tool, explaining to students how we discover objects in space, how we determine their composition using spectroscopy, how we calculate their orbits, and how we think about the physics of comets. It's a real example, happening in real time, that students can connect with directly. Instead of learning about comets as historical objects studied in the past, they can learn about a comet that's being studied right now, in their own lifetime. That kind of immediacy and relevance makes education more engaging and memorable. Let's also think about what 3i Atlas tells us about the diversity of the universe. Before we knew about interstellar objects, you might have assumed that most comets are produced in situ, born in the region around their star system and trapped by gravity. But now we know that comets can be created in one star system and travel to another. This suggests a universe that's more dynamic, more interconnected, with material constantly flowing and mixing between different regions of the galaxy over vast timescales. It's a reminder that our solar system isn't an isolated island. It's part of a much larger galactic community. The infrared observations of 3i Atlas provided some of the most detailed information about its composition. The James Webb Space Telescope, which observes primarily in infrared light, can see through dust and measure the heat signatures of different molecules. When JWST observed 3i Atlas, it detected not just the major components we've mentioned, but also rarer compounds that help us understand the chemistry of the comet's nucleus. The spectral data from these infrared observations is like reading a chemical fingerprint. It tells us exactly which molecules are present, in what proportions, and in some cases, what their temperatures are and how they're changing over time. One of the most intriguing aspects of studying 3i Atlas is trying to understand its origin story. Did it form around a star in the Sagittarius region where we see it coming from, or did it form elsewhere and get ejected by some gravitational interaction, travelling through space for billions of years before arriving at our doorstep? The speed at which it's travelling, 58 kilometers per second, suggests it's been travelling for a very long time. Objects that have been drifting through space accumulate energy from galactic processes, and their speeds tend to reflect this long history. Another possibility that astronomers have considered is whether 3i Atlas might have originated in a globular cluster, a dense, ancient spherical collection of stars. Globular clusters are thought to be among the oldest structures in our galaxy. Gravitational interactions in these dense environments can eject objects at high speeds. If 3i Atlas originated in a globular cluster, that might explain its extreme speed and its age, which we estimated could be billions of years older than our solar system. The close encounters that 3i Atlas will have with planets in our solar system, even though they're, still huge distances away in cosmic terms, are interesting from a physics perspective. When a comet passes close to a planet, the planet's gravity can affect the comet's trajectory. In the case of Mars on October 3rd, the gravitational effect was minimal because the comet and Mars were moving at such high speeds relative to each other that there wasn't much time for gravity to work. But with the upcoming passes by Venus and Earth and Jupiter, each encounter will affect the comet's trajectory slightly. After it leaves our solar system, the net effect of all these gravitational encounters will have changed the comet's path through the galaxy. In a sense, our solar system leaves a gravitational fingerprint on everything that passes through it, subtly altering the trajectories of interstellar visitors forever. The question of what 3i Atlas might represent for the future of astrobiology, the study of life in the universe, is worth considering. If comets can travel between star systems, then it's theoretically possible that organic compounds or even hardy microorganisms could hitch a ride on one of these icy travellers. Now, the journey through space is harsh. Radiation from cosmic rays would likely destroy most forms of life, or at least damage DNA severely. But certain extremophile microorganisms on Earth, organisms that live in the most extreme environments we know, in boiling hot springs, in Arctic ice, in deep ocean vents, have shown remarkable resistance to radiation and can survive in simulated space conditions for extended periods. Could microbial life from one star system potentially colonize another by riding on comets? It's speculative, but it's a possibility that some scientists think is worth considering. But let's be clear, there's no evidence that 3i Atlas carries life. This is purely theoretical speculation. The comet has been studied carefully, and nothing has been detected that suggests the presence of living organisms. Astrobiologists do find it interesting, though, that the chemistry of 3i Atlas includes organic compounds and a diversity of elements that could potentially support life. The presence of carbon dioxide, water, carbon monoxide, and the complex cyanide compounds all suggest a rich chemistry that could, under the right conditions, create or sustain life. But again, this is potential, not proof. The role of citizen scientists and amateur astronomers has been important in monitoring 3I Atlas. While professional astronomers with access to major observatories have made the most significant discoveries, amateur skywatchers with decent telescopes have also contributed observations. They've helped track the comet's brightness changes, confirm observations made by major telescopes, and in some cases have spotted details that were then followed up by professionals. This collaborative approach, where professional and amateur astronomers work together toward common goals, has become increasingly important in modern astronomy. There's simply too much sky to monitor and too many objects to study for professionals alone. As we look toward the future, 3I Atlas's legacy will likely include spurring investment and interest in interstellar object detection and study. Governments and research institutions are likely to allocate more resources to surveys designed to find these objects, and more thought is going into how we might eventually study them in greater detail. There might be proposals for spacecraft missions to intercept interstellar objects, collecting samples and sending them back to Earth or analysing them remotely. There will certainly be more ground-based and space-based observational campaigns. Each interstellar object we study will teach us something new. In the broader context of humanity's relationship with the cosmos, 3I Atlas represents something profound. It's a reminder that we live in a vast, interconnected universe, where objects and materials travel between stars, where our solar system is part of a larger galactic community, and where we have the capability to detect and study these cosmic visitors. Just a century ago, we didn't know that other galaxies existed beyond our Milky Way. A few decades ago, we didn't know that planets existed around other stars. Just a few years ago, we didn't know about interstellar objects. Each of these discoveries has expanded our understanding of our place in the universe and has changed how we think about the cosmos. 3I Atlas is a comet that came from the stars, travelled billions of years through the darkness of space, and for just a brief moment in cosmic time, a few months in 2025, passed through our neighbourhood where we could see it and study it. By December 2025, it will be on its way back out to the interstellar medium, carrying with it the memory of its encounter with our solar system. Someday, perhaps billions of years in the future, it might be captured by another star's gravity and settle into another planetary system, and the cycle will continue as material flows through the galaxy, telling the story of the universe's long history and vast interconnectedness. The study of 3I Atlas matters because it teaches us about the universe. It teaches us about how material is distributed in our galaxy, about the chemistry that exists in different regions of space, about the processes that form planets and comets around other stars, and about the dynamic nature of the cosmos. Every piece of data collected, every observation made, every analysis performed contributes to our collective understanding of the universe and our place in it. And that understanding, that knowledge of the cosmos, is something that enriches human consciousness and connects us to something larger than ourselves, the vast, beautiful, mysterious universe that we inhabit. The night sky has always held a special place in human culture. For thousands of years, people have looked up at the stars, wondered about what's out there, created mythologies and stories to explain the lights in the darkness. Then came the scientific revolution, and we started to understand the stars and planets and comets through the lens of physics and chemistry. Then came telescopes, giving us new eyes to see farther and clearer. Then came spectroscopy, allowing us to understand what stars are made of. Then came space travel, and we were able to leave our planet and walk on other worlds. Then came space telescopes, freed from Earth's atmosphere, able to see the universe in unprecedented detail. And now we have the capability to detect objects that have travelled light years through space to pass through our solar system. 3I Atlas is part of this grand story of human discovery and exploration. It's a reminder that the universe is full of surprises, that there's still so much we don't understand, and that science is an ongoing process of asking questions, making observations, and refining our understanding based on evidence. Some mysteries about 3I Atlas remain unresolved. Some scientists maintain a healthy skepticism about whether we've fully understood all its unusual properties. Others are confident that we have good natural explanations for everything we've observed. The truth will likely emerge over the coming years and decades as more data is collected and analysed, As new interstellar objects are discovered and studied, and as our models of comet physics and interstellar chemistry continue to evolve, what we can say with certainty is that 3I Atlas is real. It came from outside our solar system, and it has taught us something new about the universe. Whether future discoveries reveal additional mysteries or confirm our current understanding, the comet has already changed how we think about the cosmos. It's one more piece of evidence that the universe is far more interesting, far more diverse, and far more interconnected than we might have imagined just a few years ago, and that ultimately is what makes 3I Atlas special. Not just the unusual properties of the comet itself, but what it represents. A messenger from the distant universe, telling us that we're not alone in the cosmos, and that the stars and space between them are full of stories waiting to be discovered. The Vera C. Rubin Observatory and the next generation of discovery. While 3I Atlas captured the imagination of astronomers and the public throughout 2025, something equally revolutionary was happening in the mountains of northern Chile. On July 4, 2025, just 3 days after 3 Atlas was officially discovered, a brand new telescope opened its eyes to the universe for the very first time. This telescope, called the Vera C. Rubin Observatory, had been under construction for more than 2 decades, waiting for this moment. And when it finally began its observations, it did something remarkable. It captured images of 3I Atlas before anyone even knew the comet existed. Let me explain what happened. The Vera C. Rubin Observatory is perched high in the Atacama Desert in Chile, on the summit of a mountain called Cerro Pachon. This location was chosen because the air there is incredibly dry and clear, with dark skies perfect for seeing faint objects in space. At the heart of Rubin Observatory is an 8.4-meter telescope, one of the largest mirrors in the world, but the truly revolutionary part is the camera attached to this telescope. This camera, called the Legacy Survey of Space and Time Camera, or LSST camera for short, is the largest digital camera ever built. Imagine if your phone's camera had 3.2 billion pixels instead of just a few million. That's how many pixels this camera has. It's roughly the size of a small car and weighs almost 6 tons, which is about much as 3 average automobiles put together. When Rubin Observatory began its first observations on July 1st, 2025, the same day Atlas discovered a 3I Atlas, the scientists operating Rubin were just testing out all the systems, calibrating instruments, and making sure everything was working correctly. They weren't even looking for 3I Atlas specifically. The telescope was just scanning a region of the sky that happened to contain the comet. Over the next 6 days, as Rubin Observatory continued its testing and commissioning phase, it took 49 pictures that included 3 Atlas, even though nobody knew yet that the comet was there. It wasn't until later, after 3 Atlas had been officially discovered by the Atlas Survey on July 1st and confirmed by astronomers around the world, that scientists realized something amazing. When they looked back at Rubin's early images, they discovered that Rubin had photographed the comet on June 21st, a full 10 days before anyone officially spotted it. In fact, Rubin's pictures from June 21st are the earliest high-resolution images of 3I Atlas ever taken by a large telescope. These images showed the comet farther away, before it had become as active as it would be later. They captured the comet's early activity, its young coma before it had fully developed. This was an incredible piece of serendipity, the kind of happy accident that scientists love. Rubin Observatory, on its very first week of observations, had made one of the most important discoveries of the year without even trying. This discovery points to something profound about the Vera C. Rubin Observatory, and what it means for astronomy in the years to come. The observatory's primary mission is called the Legacy Survey of Space and Time. For the next 10 years, Rubin will scan nearly the entire night sky visible from the southern hemisphere almost every single night. It will take about 1,000 pictures each night, covering the entire southern hemisphere sky completely every 3 to 4 nights. These observations will create an ultra-wide, ultra-high-definition time-lapse movie of the universe, showing how the cosmos changes over time. To put the scale of this effort into perspective, Rubin will generate about 20 terabytes of data every single night. A terabyte is 1,000,000 megabytes. If you tried to download 20 terabytes of data onto your computer, it would fill up thousands of computers. Over 10 years, the total data collected will be around 500 petabytes. That's 500,000 terabytes. The dataset will contain billions of objects with trillions of measurements. When scientists analyze all this data, They'll be able to answer questions about the universe that we haven't even thought to ask yet. One of the main things Rubin Observatory is designed to find is something called dark comets. Now, when you think of comets, you probably think of those objects with beautiful, glowing tails that stream across the sky, becoming visible, sometimes with the naked eye. These are bright because they're made of ice and dust that reflects sunlight, creating those gorgeous displays. But dark comets are different. They don't produce visible tails. They're not bright and showy. They're elusive, quiet, and very hard to detect. Yet they're everywhere. The first dark comet ever identified was Oumuamua, the first interstellar object back in 2017. Oumuamua was strange because it showed signs of being active. It showed non-gravitational acceleration, meaning something was pushing on it other than the sun's gravity. But there was no visible tail, no glow, nothing you could see. It was like watching an invisible hand pushing an object across the sky. At first, scientists weren't sure what dark comets were. But over time, they've realized these objects are probably comets that have lost most or all of their bright dust and ice, or perhaps comets that were never very dusty to begin with. By 2024, astronomers had found about 14 dark comets in our solar system. But here's the remarkable part. Between 2023 and late 2024, the population of known dark comets actually doubled. Scientists found almost as many new dark comets in that 1 year as they had found in the previous several years. This explosion of discoveries suggests that dark comets might actually be far more common than anyone expected. There could be hundreds or thousands of them lurking in our solar system, invisible to current telescopes but waiting to be discovered. Scientists studying dark comets have found that there seem to be two different types. The first type is called inner dark comets. These are relatively small, about 33 feet or 10 meters across, and they orbit in the inner part of the solar system on fairly circular orbits. The second type is called outer dark comets. These are much larger, about 3/5 of a mile or 1 kilometer across, and they orbit in more distant regions on elongated elliptical orbits. Both types show the signature of having outgassing, material being released from their surfaces without producing visible bright tails. It's like seeing evidence of activity but not being able to see the activity itself. With the Vera C. Rubin Observatory now online and conducting its massive survey, astronomers expect that many more dark comets will be discovered in the coming years. The survey is about 100,000 times more sensitive than current all-sky surveys. It can see things that we've never been able to see before, and this sensitivity means that smaller objects, fainter objects, and objects moving rapidly through space, all things that dark comets typically are, will become visible for the first time. In fact, some astronomers estimate that Rubin might discover dozens or even hundreds of new dark comets over its 10-year mission. What makes this important is that studying dark comets teaches us about the early solar system. These objects are left over from the formation of our planetary system. They carry chemical signatures and physical properties that tell us about the conditions that existed when planets were forming. They might carry water that was delivered to Earth by comet impacts billions of years ago. They might contain organic compounds, the building blocks of life. By studying dark comets, we're reading chapters of Earth's own history, written in ice and rock, and travelling through space at thousands of kilometres per hour. The existence of Rubin Observatory also changes what scientists mean when they talk about searching the sky. Before Rubin, astronomers had to choose where to point their telescopes. They made observations of specific targets, specific regions of the sky that they thought might be interesting. With Rubin, the telescope is pointed at large sections of the sky, and it observes everything in that region, automatically cataloguing billions of objects and looking for anything that moves or changes. It's not searching for one specific thing, it's searching for everything that's interesting, including things we don't even know to look for yet. This is revolutionary because many of the most important discoveries throughout scientific history were things that scientists didn't expect to find. When you're ready to be surprised, when your instruments are designed to detect the unexpected, that's when amazing discoveries happen. Life on Mars and the search for biosignatures. While 3i Atlas was passing through the inner solar system and the Vera Rubin Observatory was beginning its epic sky survey, something equally remarkable was happening on the surface of Mars. NASA's Perseverance rover, a 6-wheeled robot that has been exploring Mars since February 2021, made a discovery that could fundamentally change how we think about life beyond Earth. In September 2025, Perseverance discovered mudstones in a location called Jezero Crater that contained what scientists call biosignatures, or signs of past life. Here's what Perseverance found. In the mudstones, scientists detected organic carbon and unusual textures that look very similar to structures created by microorganisms. The robot also found nodules, which are little round rocks made of iron compounds called iron phosphate and iron sulfide. On Earth, these kinds of nodules form through processes that often involve biological activity. They're not definitive proof of ancient Martian life, but they are suggestive. They raise the tantalizing possibility that billions of years ago, when Mars had liquid water on its surface, it might have also had microbial life. Jezero Crater is a particularly promising location for this discovery. Evidence suggests that billions of years ago, Jezero Crater held a calm freshwater lake. Unlike some places on Mars that might have had harsh, acidic environments where life would be impossible, Jezero seems to have had relatively hospitable conditions. The water was probably not too salty, not too acidic. The climate would have been warmer than it is today, with an atmosphere that could potentially support microbial life similar to some of the hardiest organisms we find on Earth. When Perseverance took samples from the mudstones and analysed them with its onboard laboratory equipment, the data suggested that organic compounds were present. Organic compounds are carbon-based molecules. They're not definitive proof of life. Organic compounds can be created through chemistry that has nothing to do with living things, but they're necessary for life, and their presence on ancient Mars suggests that at least some of the ingredients for life existed. The unusual textures that the rover observed, the patterns in the rock, could be what scientists call stromatolites, which are layered structures that on Earth are often created by microbial communities working together over time. Scientists are being cautious about these findings, and that caution is appropriate. Even if the biosignatures are real, interpreting them is difficult. We can't bring Perseverance into a laboratory and do more detailed testing. We're limited by what the rover's instruments can do on the surface of Mars, and scientists want to be absolutely sure before making claims about finding extraterrestrial life, because such a claim is one of the most profound statements you can make in science. It would mean that life arose independently in at least 2 places in the solar system, which would suggest that life is probably common throughout the universe. But the discovery does show that the building blocks and conditions for life existed on ancient Mars. It adds to a growing body of evidence that Mars was once a much more habitable place than it is today. The findings from Perseverance, combined with observations from the Curiosity rover and from orbiters around Mars, paint a picture of a younger Mars that was warmer, wetter, and much more Earth-like than the cold, dry desert we see today. Something changed. Mars lost its magnetic field, and without that protection, the solar wind stripped away much of the atmosphere. The climate became harsher, the water disappeared, and any life that might have existed went extinct or adapted to survive beneath the surface. These discoveries from Perseverance are important because they help us understand not just Mars but Earth, and the possibility of life elsewhere. They tell us that the conditions necessary for life can arise on planets other than Earth. They suggest that microbial life, at least, is relatively hardy and capable of existing in a variety of environments, and they motivate the search for signs of life on other worlds, whether that's Europa, the ice-covered moon of Jupiter, or Enceladus, the ice-covered moon of Saturn, or places far beyond our solar system. Exoplanet discoveries and the search for habitable worlds. While Perseverance was studying Mars, the James Webb Space Telescope and other observatories were making remarkable discoveries about planets orbiting other stars. One particularly intriguing exoplanet that has captured scientists' attention is called K2-18b. This planet orbits a red dwarf star, a small, dim star that is about 124 light-years away from Earth. In cosmic terms, that's right next door. K2-18b is unusual because it seems to be roughly 8.6 times the mass of Earth and 2.6 times Earth's diameter. This puts it in an interesting middle ground. It's too big to be classified as an Earth-like rocky planet, but too small to be classified as a gas giant like Jupiter. Scientists sometimes call these planets super-Earths or mini-Neptunes, depending on their composition. What makes K2-18b particularly exciting is that it orbits within the habitable zone of its star, the region where a planet could potentially have liquid water on its surface. When the James Webb Space Telescope analysed the light filtering through K2-18b's atmosphere, it detected several interesting molecules. The atmosphere contains carbon dioxide, methane, and possibly water. These are gases that on Earth are associated with biological processes, though they can also be produced through purely chemical means. Scientists are debating what K2-18b is really like, and whether it could possibly harbour life. Some researchers have suggested that it might have an ocean of liquid water beneath a thick hydrogen-rich atmosphere, making it a kind of water world with an alien sky. Others are more sceptical, pointing out that we have limited data and many unknowns. The excitement around K2-18b highlights an important aspect of modern astronomy. We now have the capability to analyse the atmospheres of exoplanets and look for signs of potentially habitable conditions or even biosignatures. This would have seemed like pure science fiction just a few decades ago. Now, using telescopes like James Webb, which can detect the faint light filtering through an exoplanet's atmosphere as the planet passes in front of its star, we can measure the chemical composition of worlds that are dozens or hundreds of light years away. We can't visit these places, but we can read their atmospheres from billions of kilometers distance. In 2024, citizen scientists and professional astronomers working together confirmed the discovery of two new exoplanets, TIC 39381.343b and TIC 241295330b. What's remarkable about this is that amateur astronomers with telescopes and equipment in their backyards contributed to these discoveries. They made observations of the stars hosting these exoplanets, watching for the tiny dips in brightness that occur when the planet passes in front of the star. These transits are the primary way we discover and study exoplanets, and citizen scientists have proven invaluable in providing observations and data that help confirm discoveries and refine our understanding of these distant worlds. The work being done to study exoplanet atmospheres is part of a broader mission to understand whether life beyond Earth is common or rare. If we find that many exoplanets have atmospheres suitable for life, with water and organic compounds, then we might infer that life is probably common throughout the universe. Conversely, if habitable exoplanets turn out to be rare, then Earth might be more special than we thought. Either way, the knowledge we gain changes how we understand our place in the cosmos. Dark matter, black holes, and deep space mysteries. While telescopes like Rubin and James Webb focus on relatively nearby cosmic objects and exoplanets, other observers are looking at the universe's biggest mysteries. One of those mysteries is dark matter, the invisible material that makes up most of the matter in the universe. We can't see dark matter directly, but we can detect its gravitational effects. The Vera C. Rubin Observatory is named after Vera Rubin, an astronomer who provided some of the first convincing evidence for the existence of dark matter back in the 1970s and 1980s. Her work showed that galaxies were rotating in ways that couldn't be explained by the visible matter alone, the stars, gas, and dust we could see. There had to be more matter, invisible matter, pulling on the galaxy and affecting its motion. That invisible matter was dark matter. In 2024, astronomers made a remarkable discovery about black holes. They identified a black hole called Gaia BH3, which is the most massive stellar mass black hole found in the Milky Way galaxy. Stellar mass black holes are created when massive stars explode as supernovae and their cores collapse into black holes. They're typically somewhere between a few times and a few dozen times the mass of the Sun. But Gaia BH3 broke the mold. This black hole is nearly 50 times the mass of the Sun, making it the most massive stellar mass black hole ever found in our galaxy. Its existence challenges our understanding of how black holes form, because current theories suggest that black holes this massive shouldn't be produced through the normal death of a star. The discovery of Gaia BH3 raises intriguing questions. How did this black hole become so massive? Did it merge with other black holes? Did it accrete massive amounts of material from a companion star? These questions point to gaps in our understanding of stellar physics and black hole formation. Every discovery like this is an opportunity to refine our theories and develop better models of how the universe works. Scientists have also been studying the supermassive black hole at the center of our galaxy, called Sagittarius A. In 2024, astronomers captured polarized light images of Sagittarius AT, images that revealed the magnetic field around the black hole and hints of a hidden jet of energy being ejected from it. These observations help us understand the environment around the most extreme objects in the universe. Black holes are natural laboratories where gravity becomes so intense that the rules of physics operate differently than we're used to. By studying black holes, we're testing our understanding of gravity and space itself. Comets across the solar system. 3I Atlas wasn't the only comet making news in 2024 and 2025. Another bright comet called C2025A6, discovered by scientists using an observatory named Lemon, was also generating excitement. In fact, for much of 2025, the brightest comet in the sky was the one that had been discovered in 2023, called C2023A3, nicknamed Tsuchinshan Atlas after the observatory that spotted it. This comet became the brightest comet of the decade. Amateur and professional astronomers around the world tracked these comets, observing how their brightness changed, how their tails evolved, and measuring their chemical composition. In late 2024, astronomers documented multiple outbursts of a comet named 12P Ponce-Brooks. Outbursts are episodes where a comet suddenly becomes much brighter, often caused by chunks of its nucleus breaking off or by sudden increases in outgassing. These outbursts make comets more visible and give astronomers opportunities to study them in greater detail. The tracking of comets like these, whether by casual observers or by professional astronomers, contributes to our overall database of knowledge about how comets behave and evolve. Through 2024, citizen scientists made over 1,563 observations of comets. These observations helped scientists understand comet behavior, track changes in their activity levels, and document rare events. One comet observed in July 2024 was tracked as it passed near Mars, much like 3I Atlas would do in October 2025. These observations showed that our solar system is teeming with these icy wanderers, some bright, some dim, all carrying stories about the early formation of our planetary system. The population of near-Earth asteroids beyond comets. The solar system is also full of asteroids, and several significant discoveries and developments occurred in 2024 and 2025 regarding these space rocks. One asteroid that made headlines was 2024 YR4, which was discovered in December 2024. When it was first discovered, calculations suggested that this asteroid had a small but significant chance of striking Earth on December 22nd, 2032. At one point, the impact probability was assessed at more than 1%, which might sound small but is actually quite high by planetary defense standards. However, as astronomers continued to observe the asteroid and submitted more data to the Minor Planet Center, which is the official repository for asteroid observations worldwide, the threat assessment changed. Additional observations refined the calculations of the asteroid's trajectory, and by February 2025, NASA announced that the impact probability had dropped to just 0.28%. With continued observations and analysis, the probability continued to decrease further. By late 2025, 2024 YR4 was no longer considered a significant threat to Earth. This story illustrates an important aspect of planetary defense. Even when an asteroid is initially identified as having an impact potential, continued observations typically refine our understanding and reduce the perceived threat. More data leads to more accurate predictions. Another asteroid called 2025 QV5 was discovered in late August 2025 and made a close approach to Earth on September 3rd, 2025. The interesting thing about 2025 QV5 is its orbital period. Calculations suggest that it won't come anywhere near as close to Earth again until September 4th, 2125, approximately 100 years later. This is a remarkable coincidence of orbital mechanics, where the paths of Earth and 2025 QV5 align in such a way that close approaches occur at century intervals. Of course, this prediction assumes that 2025 QV5 isn't perturbed by gravitational interactions with other asteroids or planets in the intervening 100 years. The presence of an undiscovered asteroid in the asteroid belt could nudge 2025 QV5 bus slightly off course, changing when or if it will return. Asteroid 2025 TF earned the nickname of a sneaky asteroid because it zipped past Earth on September 9, 2025, coming within just 428 kilometers of the surface, passing above Antarctica. The remarkable part is that it wasn't detected until after the close approach. This asteroid was only about the size of a small car. Its discovery after passing so close to Earth highlights the reality that space is vast, and even asteroids on collision courses with Earth can sometimes pass undetected, especially if they're small. The monitoring and cataloguing of near-Earth asteroids is an ongoing effort. NASA's Center for Near-Earth Object Studies tracks thousands of known asteroids and is constantly searching for new ones. The risk of a major impact is low at any given time, but over long timescales, impacts do occur. Having good tracking and detection systems helps us understand the threat and potentially take action if a dangerous asteroid is ever discovered heading toward Earth. The future of solar system exploration. Looking ahead to the years beyond 2025, the solar system promises to remain a dynamic place of discovery and exploration. NASA's Lucy mission is exploring Jupiter's Trojan asteroids, a collection of ancient rocky bodies that orbit in regions ahead of and behind Jupiter. The mission will fly past asteroid 522246 Donald Johanson on April 20th, 2025, while on its way to study the Trojan asteroids. These asteroids are thought to be leftover material from the formation of the solar system, and studying them will teach us about conditions in the early solar system when planets were forming. NASA's ambitious Artemis II mission, which will send 4 astronauts on a 10-day journey around the Moon, was targeted for launch no earlier than September 2025. When it launches, it will represent a significant step in returning humans to the Moon. The successful completion of Artemis II will pave the way for future lunar missions, including the establishment of a sustained human presence on the Moon. India's Chandrayaan-3 mission made a successful landing on the Moon in 2024, marking India's first lunar landing. Japan's SLIM mission also achieved a historic lunar landing. China's Chang'e 6 mission retrieved samples from the far side of the Moon, another tremendous achievement. These international efforts show that lunar exploration is becoming an international endeavour, with multiple spacefaring nations making contributions and discoveries. The discoveries and missions of 2024 and 2025 paint a picture of a dynamic, diverse universe teeming with interesting objects and phenomena, from the Interstellar Visitor 3 Atlas with its mysterious reverse tail to the Vera C. Rubin Observatory opening new eyes to the cosmos, to Perseverance's intriguing biosignatures on Mars, to exoplanets orbiting distant stars and the mysterious dark matter permeating the universe. We live in a golden age of astronomical discovery. Every day brings new information, new questions, and new possibilities. The universe is far more interesting, far more populated with diverse objects, and far more interconnected than we could have imagined just a few years ago. And we're only just beginning to scratch the surface of understanding it all. The next few years promise to bring even more remarkable discoveries that will continue to expand the boundaries of human knowledge and reshape our understanding of the cosmos.